Hello and welcome to a lesson on systems of equations and solving them by graphing. So before we get to solving a system, we have to know what it is. And so a system of equations is basically when you're looking at two or more equations at the exact same time. And generally, these are going to be multiple variables, multiple equations, okay? So a system is a set of two or more equations. So like in this module in particular, we're going to be focusing on what we call linear systems. So instead of looking at one line and maybe what's the slope of the one line or what's the y-intercept of the one line, let's look at these two lines together and let's try to see what they have in common when we're looking at them at the same time. Okay, so when you're dealing with the system, again, two or more equations considered at the same time, you're going to have a variable for each variable you have, you're going to need an equation. So for each variable or unknown in your system, there must be an equation. So if you're looking at a 2 by 2 system, that's this first example here, that's a 2 by 2 system. You have two variables, you need two equations in order to be able to find the solution or to solve that system. You could have three variables, in which case you'd need three equations, and so this would be a 3 by 3 system. And these systems can become quite large. Luckily, like I said, we're going to be focusing on 2 by 2s, so nothing to stress about here if that looks a little intimidating, okay? And actually, it's not so bad, but we are going to focus on 2 by 2s. So what is a solution to a system going to look like? Well, the solution to a system, again, it's what the two equations in our case what the two equations are going to have in common. And so your solution to your system contains a solution for each variable in that system. And remember, when we plug in a solution, it has to make a true statement. So the solution to a system has to make all of the equations true when it's plugged in. So for instance, the system I showed you just a second ago has a solution at 12, 6, and we could verify this by plugging into both equations. So we're going to plug the 12 in for x, we're going to plug the 6 into y. So let's go with this first one. 3 times x, which is 12, minus 4 times y, which is 6, should equal 12 if this is the correct solution. So that's 36 minus 24, and that does in fact equal 12, so that's good. And that's the first one here. Let's say we plug into the second one. It's got to make both true. So in the second one, it says y, which is 6, should equal x, which is 12 minus 6, and in fact 6 does equal 6. So since we get a true statement for both when we plug both in, because that's true and that's true, that's verified that this is the solution. Okay, so we can verify a solution in that way. And most of our linear systems are going to be what we call consistent systems. And in a consistent system, you have distinct solutions, and so it's going to be one distinct solution for our linear system. And it is possible, however, that we don't have a consistent system. It's possible that you have a system that has no solutions, in which case we would call it an inconsistent system. And then it's possible that your system has an infinite number of solutions, in which case we would call it a dependent system. Okay, now again, we're going to focus on linear systems. So a linear system is one that contains only linear functions. So you're looking at two variables, two equations, and both of those equations are linear. Now it could be that they're in slope-intercept form, it could be that they're in standard form, but you're going to have an x and a y to the first power, so it's a linear system. And the solution to a linear system is going to end up being the point where the two lines would cross on the graph. Which should make sense if you're thinking about two lines and what they have in common. What they're gonna have in common on a graph they're gonna be points where those two lines cross. Okay, and because it's a point where the lines cross, and because it has to contain a value for each variable, you're going to have an x and a y in your solution. So your solution is going to be a point where they cross. It will contain an x value and a y value that makes both equations true. And again, there are three behaviors for a system, and this is what it will look like if it's linear. Most of your linear systems are going to behave like this first one. If you graph two lines, they're going to cross at one point. And so this would be a consistent system with one distinct solution. So a consistent system has one solution, one point where the lines cross, and this example has one solution at -2, +1. Now again, it's possible that you have an inconsistent system. If it's linear, what's it going to look like if two lines never cross? Well, they're going to be parallel. So an inconsistent system is going to have parallel lines. An inconsistent linear system will have parallel lines. So therefore, no points of intersection. That means no solutions to the system. And remember what's going to happen with our lines if they're parallel. Notice that the slope here is 3 and the slope here is 3, but they're crossing at different places on the y-axis. So we have parallel lines, the same slope, different y-intercepts. They're never going to cross. Okay, and then lastly, you can have a dependent system. So it's hard to tell here on the picture, but I graphed y equals -2x plus 3, and I graphed that again, and it's the same line twice. So we can look at the same line 2 times, write it down 2 times, and call it a system. And what's going to happen is they're going to overlap at every single point. So a dependent system means you have the exact same equation, the exact same line twice. The exact same line twice. And so there's an infinite number of solutions because these lines overlap or they share or they have in common every single point. So they have an infinite number of solutions. Now they're still distinct. You can't just put in any point. Obviously, there's only the points that are on the line that are going to be solutions to that system, but those lines will go on forever, so the solutions are infinite. Okay? So that's sort of the concept behind a system, but we need to be able to solve. Now, I think the most intuitive way to solve a linear system, because we're looking for the point where the lines cross, would be to graph. If we can graph our 2 lines and find the point where they cross, we will have the solution to our system. And so we are going to look at solving by graphing. Again, it's, in my opinion, the most intuitive way to solve, but it's not always the most efficient or effective way. And you could imagine graphing 2 lines, if the point of intersection is not a precise point. So let's say that the solution was something like 1/3 and -3/4. Now, if we're graphing these lines, I'm not going to be able to tell that point is exactly at 1/3 and -3/4. So it's not always efficient, but it is very intuitive. So really, this should only be done if both equations are in an easily graphable form. So if they're both in slope-intercept form, oops, I'm putting the words easily and graphable together. If it's in an easily graphable form. So if they're both in slope-intercept form and it's easy to identify the slope and intercept to graph, or if they're both in standard form and it's easy to identify the x and y intercepts, whatever. If it's easily graphable, then this would be good, but it's also only effective if the solution is a precise point. So you can maybe have easily graphable forms, but when they cross, and this would depend too on how neatly you're making your graph. If you can't tell exactly where they're crossing based on your graph, then this is probably not going to be the best way to solve. At least by hand, okay? So fortunately, this can be done using technology or Desmos in addition to doing this by hand, but I'm going to show you both ways, okay? So Desmos is going to in fact work for, or technology will work for any of these systems, whether they're easily graphable or the solutions are precise or not. But if we're doing this by hand, okay, we want it to be something that works out kind of nicely. So I picked one that works kind of nicely here. Let me show you this example by hand, and then I'll show you how to use technology so that it's precise no matter what. So let's call this equation 1. Equation 1, I can see the slope, that's my number in front of x here, is 1. So 1/1. And I can see my y-intercept, that's b, is -5. So that's telling me to begin on the y-axis at -5. So 1, 2, 3, 4, 5. And from there, I can go up 1 and right 1 and make another point. So up 1, right 1, I can make another point. And in fact, I can make as many of those as I want before I try to connect the dots here. Sometimes that's easier said than done. And yeah, see, I totally missed. Okay, let's go with 3 times no, that's terrible. It's a little bit better. Do you see my struggle here? There we go. That's not too bad. Um, if you're doing this on paper, you don't have to try to rely on technology for that piece. Okay, so there's the first one. Let's look at the second one. I'm going to call that equation 2. Equation 2, I can see my slope is a negative 1/3 and that my y-intercept is 3. So that was telling me to begin on the y-axis at 3 and that I can go down 1 and right 3 to make my next point. So down 1, right 3, and again I can do that as many times as I want in order to make this graph. And if I'm graphing by hand, I want to make multiple points because I can see, just like what happened right there, sometimes I can see exactly where these two are going to cross. So I'm going to try my best. Okay, I'm going to say that's good enough. And I can already see, so because I made multiple points, that this is going to be the solution to my system. That is the one point that they both have in common. And remember, every point on a line is a solution to the line. So if that point is a solution to the red and that point is a solution to the blue, then it has to be a solution to the system. It has to be the solution when we're looking at both equations at the same time. So I can see that my solution is at the point, where is that? 1, 2, 3, 4, 5, 6, and 1. And just so we can be old, let's get a little bit of a bigger highlight on that. There we go. Okay, so that's a solution from my graph. Now, again, I picked this solution, I picked this system to work out with a very nice solution, but it doesn't always happen that way. And to be honest, sometimes graphing by hand is just, we get a little sloppy with it, and not all solutions are going to be precise. So if we could rely on technology to get us precise solutions, I say we do it. So let's practice using Desmos so we can see how easy this is. And I don't have my calculator ready. I am so sorry. Oh my gosh. I'm trying to pull my calculator up from my split screen, and you can see me struggling here. I usually already have it open, and I don't know what happened. All right. It's coming. There we go. Okay, so we're just going to type each equation in. So let's go with y equals a negative x plus 2. And let's go into a separate line to put in the next equation. Y equals 1/2 x and then minus 4. And you can see it's graphed both lines, and then just simply tapping on the point of intersection shows me the solution. So I can see from Desmos here that I have a solution at 4 and negative 2. And remember, I wouldn't do this because I very much trust my calculator here, but if you wanted to check it, you could plug 4 in for x, plug negative 2 in for y, and make sure it works. So if I plugged in negative 2 equal to a negative 4 plus 2, that's a true statement. And if I plug in negative 2 equals 1/2 times 4 minus 4, I have negative 2 equal to 2 minus 4, and again, negative 2 equals negative 2 is a true statement. So I could plug that in to verify, but it's pretty clear that the solution, or the point where those two lines cross, or the one point, or the solution that they have in common, is going to be 4, negative 2. Okay, so there's that one. Now let's look at the next one. Let's try this again. Y is going to equal 2x minus 3, and y is going to equal 1/5 x plus 6. And there it is again, my solution at 5, 7. So 5, 7 is going to be the solution here. And let me box this in. That's my solution here. Now those two, if we were to graph by hand, I think they're both in graphing form, so that's kind of nice, and we can see the solutions are precise. So those probably wouldn't have been too terrible to do by hand, but it's just faster here, right? Y equals 2/3 x and plus 1, and y equals a negative x plus 6. Gosh, okay. And there we go again. Nice, simple solutions. Points for these cross. Now again, all three of those probably would have worked out nicely by hand, but let's look at this next one. Now this, not terrible, is still something we could do, but how accurate are we going to get? I don't know. I don't want to have to even think about graphing those decimals by hand. So let's use Desmos here. 0.75x I said 5. There we go. Minus 1 minus, sorry, fat fingers, 1.5, and then y equals a negative 0.2x, and then plus 4.8. And there we go. Yeah, that solution by hand, not so much. So 6.632, right? You just can imagine. First, having to graph with those decimals wouldn't be ideal, and there's no way we're going to be able to identify that solution. I mean, we might be able to say, well, it's a little more than 6 and it's a little more than 3 if we graphed really accurately, but I just think that's going to be near impossible to capture if you're graphing by hand. Okay, so graphing is a great method, and sometimes it's okay by hand, but always okay using our technology. Okay? So there's an introduction to systems and solving by graphing. We're going to look at algebraic ways to solve as well, but for now, this should give you enough to get going on your practice assignment. So as always, if you need some extra help, just reach out. And until next time, take care.